Welcome back. Okay, so today I want to tell you about a really important distribution called the student's t distribution, which is particularly useful when you're going to do hypothesis testing, but you have a small sample size n. So we know that if we have a relatively large sample size n, then by the central limit theorem, the sum of random variables of a bunch of identical random variables will converge to a normal distribution. But for small n, there's kind of a correction that we need, and this is going to be related to the student's t distribution. So I'm going to derive kind of why we use it. I'm going to show you in Python that as n increases, the t distribution actually converges to the normal distribution you would expect from the central limit theorem. And that will be useful for hypothesis testing. T distribution is actually useful for lots of other things, but I'm thinking about it as something you need to know. If you're going to do hypothesis testing and you have a small n, oftentimes instead of a normally distributed test statistic, you're going to need a t distribution distributed test statistic. Okay, so you're going to want to set up your rejection region based on this distribution instead of a normal distribution if you have a small sample size. Okay, let's get into it. And I'll point out the student t distribution. This is actually, this paper where this was introduced was published under a pseudonym student, and that's why this name stuck. Okay, so let's jump in. So let's talk about this in the context of a hypothesis testing problem. So imagine we're testing a hypothesis. So we are testing a hypothesis. And let's say that the hypothesis is a simple hypothesis that after some manipulation or some treatment, the mean of my population has changed. We've done this before. We've looked at this kind of basic hypothesis test. So we're testing the hypothesis that after some kind of manipulation or modification, some manipulation to my system, the new parameter, the new expected value is different than the old expected value. The mean of the system, mu, has changed. Okay? So for example, maybe I have a factory and I'm outputting parts, and those parts have a certain, expected success rate of not failing. Or not being recalled or whatever, and I do something hopefully to improve the yield of my factory. That would be a hypothesis I'd want to test. Did that manipulation or modification actually change the mean of that process? Okay, and so what we would do is we'd set up a hypothesis test based on the old mean and the new data. We'd collect data from the system after the manipulation, and we test that it was the same or different than the previous mean. Okay, so what we would do is we would collect new data. I'm just setting up this t distribution by reminding you of what a hypothesis test looks like. We collect data, x1, ... to xn, and this is going to be a small n for the t distribution to matter. We collect data, and what we do is we collect a sample mean, and compute x bar, the sample mean, which is 1 over n sum from I equals 1 to n of each of these data points that we've collected. And this sample mean is our new best guess from this data set of what the mean of the system is, what the new mean mu is. And so the hypothesis that we're going to test is, does this data come from a system with the old mean, or do I refute that hypothesis and assert that this mean has changed, that this does not come from that distribution, and so thus the mean mu had to have changed? Okay, so by the central limit theorem, so we're almost to the t distribution. By the central limit theorem, x bar is going to be distributed as a normally distributed random variable with mean mu and variance sigma squared over n if nothing changed, if mean did not change. And so finally, what this means is that we can actually take our data and we can compute this mean, and we can see where that mean lives with respect to this normal distribution, and we can build a hypothesis test. We can build rejection regions based on this normal distribution, and essentially test our hypothesis of whether or not the mean did or did not change. Okay, so the hypothesis would be that these data is from this mean value. So the null hypothesis, H naught, is that the mean didn't change, did not change. And so we set up a test statistic. So the test statistic for this hypothesis is x bar minus mu divided by the standard deviation, or sorry, the standard error, sigma over root n. This should be just a complete recap for you. We take this, this new sample mean, we subtract off the old mean, divide by the old standard deviation divided by the root of our sample size. And this is a test statistic that should be normally distributed with mean 0 and standard deviation 1. So we can use this for hypothesis testing. The issue here is the following. We probably know mu because we're trying to assert the hypothesis, did mu change? Did the mean change? So we probably know this value. We know this because this is the thing we're testing, did it change or not? But we might not know the variance, sigma, of the actual underlying true distribution. We might not know this. This is like the variance of the actual full distribution that we don't know. We don't know. This is unknown, probably. If it is known, just use this formulation. If it's unknown, if this sigma is not known, then we have to do what's called bootstrapping. So in that case, we have to bootstrap, and we replace this unknown standard deviation with the standard deviation of our data, what's called the sample standard deviation. And so that's what I'm going to write down here. So if we don't know this, then what we do is we replace this with x bar minus mu over this thing called Sn divided by root n, where Sn, essentially Sn squared, is the sample variance. It's the variance of all of my data, which is equal to the sum from I equals 1 to n of xi minus x bar squared. Okay, this is just the definition of the sample variance. So let's just zoom out, okay? We're doing a hypothesis test that the mean changed, did or did not change. And by the central limit theorem, we've derived all this before. This is the test statistic we usually use. In all of my previous lectures, we've used this test statistic, the new mean minus the old mean divided by the standard deviation over root n. That's normally distributed. You can do hypothesis testing. You can literally build, from your normal distribution, you can build a rejection region. Let's say I want a 5%, 0.05 p-value rejection region, and you can see, does this test statistic live in that rejection region or outside of that rejection region? If it lives anywhere else, then that means the mean did not change. But if it lives in this rejection region, then the mean did change, probably, within that significance, that statistical significance. But this assumes that you know the variance, the standard deviation sigma of the actual underlying distribution of the system. We often don't have access to that, and so we have to estimate that sigma from the data we collected. So if you estimate that sigma from the data we collected, that's called a bootstrap estimate, and you replace this true sigma standard deviation with a sample standard deviation computed from the sample variance. This distribution here, this variable, is distributed as the t distribution with n degrees of freedom, or t of n. Sometimes we say this is t with parameter n degrees of freedom. Okay, so that was a lot to get to introduce the t distribution. But what this means is that if you don't know the variance, the true variance sigma, standard deviation sigma, you have to replace it with the bootstrapped sample standard deviation, and that is distributed as a t distribution. Now, proving this is quite challenging. I'll show you kind of why this is true in the next video, like why this is a t-distributed random variable. We'll talk about why that's true, but just for now, you have to know that if you use the bootstrap standard deviation, you actually have a t-distribution, not a normal distribution. Now, the good news is for large n, for moderately large n, like n 30, 50, 100, anything kind of bigger than 30, this distribution starts to look so close to a normal distribution that you can just kind of ignore this and use our normal, easy test statistic up here. But if you have small n and a bootstrapped variance or standard deviation, you have to use the t-distribution, okay? So now what I'm going to do is I'm going to show you a Python code that actually just computes the t-distribution for lots of n and plots them against the normal distribution so you can see the convergence. Then we're going to write down the actual probability density for this t-distribution, and then we'll conclude with some parting thoughts. Really what I want you to know, though, is if you're doing hypothesis testing and you have a bootstrapped standard deviation or variance, and you have a small n, you need to use the t-distribution. That's the upshot. Okay, let's now plot that the t-distribution converges to the normal for large n, okay? So this is a pretty easy Python code. Essentially what we're going to do is we're going to generate a bunch of t-distributions with different degrees of freedom. So 1 degree of freedom, 2 degrees, 5, 10, 30, 100. And we're going to plot all of those student t-distributions against a standard unit normal that we think is a good approximation for big N. So we're going to do this. We're going to run it. And this is essentially, this is the plot with good colors. This shows, so kind of the white dashed curve at the very top is the standard normal distribution. And you can see from kind of dark blue up to lighter yellow, as n increases, the t-distribution gets closer and closer and closer to that normal distribution, okay? So again, what this means is that for large n, even if I have to bootstrap the standard deviation or the variance, I'm probably fine using a normal approximation. But for small n, there's a big enough difference, I might get into trouble. So I need to use the t-distribution if I have small n and I'm bootstrapping the variance. Good. That was a really quick demo. And so now kind of parting thoughts here. I guess I should actually write down the probability density for this t-distribution, but I will write down the thing that I think is really important, which is how you use this for hypothesis testing. So let's say I have my Gaussian distribution in pink, and let's say I have my t-distribution for a small n in blue. It somehow looks kind of like this. It's got fatter tails and a lower, you know, kind of middle of the distribution. So blue, this is my t. Pink, this is my normal. Okay, this is just a rough sketch. If you're doing a hypothesis test where you would normally build like a one-sided rejection region on the normal distribution, but you have a small n and you're bootstrapping your variance for your test statistic, then you need to define your rejection region based on this t-distribution, this blue distribution here, because especially where the rejection region lives, that's where the tails are, where these distributions disagree the most. So for small n and bootstrapped variance in your test statistic, you have to use the t-distribution for that, that hypothesis test to reject that hypothesis. I realize I completely flipped the colors here. Pink here is t, whereas blue here is t, and vice versa, but you get the idea. Okay, let's actually write down the PDF for the t-distribution. So the probability density function for the t-distribution with n degrees of freedom, this is a t with n degrees of freedom, is the following. I'm going to write this down. It's going to be a mess. We're going to come back and show kind of roughly why this is the way it is. It's equal to this gamma function evaluated at n plus 1 over 2. Remember, gamma is related to factorial, Specifically, gamma of an integer is equal to n minus 1 factorial for integers. But this gamma function generalizes the notion of a factorial to any number. You can take the gamma of pi or 1/2 or whatever, and it generalizes the notion of a factorial. This is a pretty complicated function. It's recursively defined based on an integral, but in statistics, it comes up all the time. And just remember, it's a function. You plug in a number, you get out another number. It's this divided by root n pi gamma of n over 2. We essentially need this to normalize the probabilities. These are just numbers. Doesn't really matter. This is a constant scaling factor. The thing that actually matters is 1 plus t squared over n to the minus n plus 1 over 2. Okay? And I'm not going to prove this, but if I take the limit as n goes to infinity, this starts to look a heck of a lot like e to the something. This looks like an e to the t squared. It's going to look a lot like a normal distribution, a standard unit normal centered at 0. So already, this is just a normalizing factor to make sure the probability adds up to 1. This is already looking like as n goes to infinity, this is going to converge to the normal distribution. You could actually write this down and prove that. That would be a nice, easy thing you could do. But this is the distribution you have to use for hypothesis testing when you have a bootstrapped variance for your test statistic and you have a small n. Okay, thank you.